I can see that clearly now, okay? Good. And I will have to tell you to flip the screen, right?
Okay, so I hope by now you all know who is the speaker. We have been fighting for quite some time. So, Professor Larry McLaren from the University of Washington at Seattle. Professor McLaren, please.
Okay, thank you very much. As you have to remember, it's very early in the morning for me here. I'm from the West Coast. It's about 3 in the morning. What I'm going to talk to you about are properties of organic matter. But before I do that, I want to say some nice words about Bikosh. I really wish I was in India to see my good friends there and honor the accomplishments of Bikosh. There were some problems in getting a visa which were not solved in time. My friendship with Bikosh began in 1986 at the Asilomar Port Matter meeting. Can you hear me clearly? Okay. Over a number of drinks of good Scotch whiskey, Bikosh told me of his plan to organize a series of meetings in India, the International Conference on the Physics and Astrophysics of the Corpuscular Plasma. I helped Bikosh by getting some funds for support of Americans to attend the meeting. The first such meeting was held at the Tata Institute in 1988. Through the time of the series of the meetings, our friendship grew. Bikosh developed a strong experimental and theoretical effort throughout India, which involved organizing experimental efforts at both BNL and CERN. He supported and developed scientific activity throughout India. This is an outstanding scientific effort that has produced many important scientific results and brilliant young scientists, and would not exist if it were not for Bikosh Sinha. Next page. Bikosh's scientific accomplishments, I think one of the reasons we met was I had an interest in photon production from the corpuscular plasma at that time, and Bikosh had written some early papers on this, and the seminal paper in this was his first paper on the corpuscular plasma, universal signals of the corpuscular plasma. The abstract that says that it's shown that the ratio of production rates of photon to muon pairs and pions to muon pairs from the corpuscular plasma are independent of the space-time evolution of plasma fireball, and thus are universal signals of the corpuscular plasma. And the basic idea was pions reflect entropy, which is conserved in slow expansion, late in the collision. Energetic photons and electrons made early and are made early and do not rescatter. And this was the basis of really a lot of work in the Calcutta group. It showed up in the experimental program at RIT, where the Indian group was involved in making a lot of the material for photon detection. And then it's generated a series of seminal papers, and that's important work. The seminal papers are summarized in a nice review, electromagnetic probes of the corpuscular plasma with Johnny Allen and Sibaji Raha. In addition to this, the work which I know of Bikosh, which is just one work, which many of us thought about at the time, was cosmology, and that's a consequence of a first order phase transition that exists for the corpuscular plasma, the hadronic matter, and the possibility of making strange quark matter in such a transition. And this is fun work, and many of us worked on problems like this, and it's interesting and it's neat. And these are scientific subjects which we share an intellectual interest. But in the end, my friendship with Bikosh is simply because we are friends, because we like one another, and that's all that's important. And that's all that ever should be important for friendship. Okay, so what I'm going to tell you about is work which is done in collaboration with a variety of authors: Rob Sarsky, Toro Kocho, Yoshinasa Hidaka, Sanjay Reddy, Kisong John, Diana Morty, Saul Hernandez, Kenji Fukushima, Yuki Fujimoto, and Mike Prasilovich. And it stems from some experimental observations which concerned, well, the experimental observations are basically the radii and masses of neutron stars. And that's coming from a variety of different data, most notably the recent data from LIGO and neutron quark collisions. And the surprise to my mind in this, the big surprise, was that taking this data together and using the equations of hydrostatic equilibrium to predict the relation between mass and radii, you get a truly excellent determination of the equation of state of strongly interacting matter at 0 temperature and baryon densities up to 8 times nuclear matter densities. This is really, truly remarkable that from just observations of neutron stars, you get such a good determination of the equation of state. In a later slide, I'll show you some results of such determinations. But the conclusion of these determinations is quite interesting. The equations of state must be very hard, and the sound velocity square turns out to be greater than or the order of 1/3, and only a few times nuclear matter densities. And this is not what one expects from a phase transition. If you have a first order phase transition, you expect the sound velocity to go very small for a while the phase transition exists. A second order, it should dip into that. So getting something where the sound velocity rises very rapidly, and it becomes relativistic, and it happens at only a few times nuclear matter densities, is really, really remarkable. It's remarkable because when you think about ordinary nuclei are a good approximation made of slowly moving neutrons and protons. And you squeeze them out only a few times, and it becomes relativistic. And you're squeezing it out by only a few times corresponds to changing the distance scales by only about 50% or something. Okay, well, what's the region where we're trying to study for neutron stars? There's one cartoon for the region of various properties of matter, defining temperature and density. Most of you are used to thinking about what happens at 0 baryon density and increasing temperature. That's the region of the high energy heavy ion experiments at, say, RIC and LHC. It's the region which is studied by lattice gauge theory, and we know much about that. On the lower part of the axis, the lower axis is what happens as you increase the baryon density at 0 temperature. And in fact, very little is understood there. There are many conjectures, but nothing is really known with great conviction. That's because lattice gauge theory methods don't work very well there. Until recently, we didn't have much experimental evidence, information at baryon densities larger than 2 or 3 times nuclear matter densities. And the methods of nuclear physics, non-relativistic nuclear physics, work up to about 2 times nuclear matter densities. So on this plot, almost all of the stuff there to the right is conjecture. And I'll talk about a conjecture which provides a natural explanation of the equation of state of nuclear matter as seen in neutron stars. And what I'm going to try to do is give you a presentation which kind of explains the qualitative details of why one has a very hard equation of state. Okay, next slide. But first I want to show you a determination of sound velocity squared from doing multi-parameter fits of equations of state to neutron star radii and masses. And you see at nuclear matter density, the sound velocity square is probably something like about 0.04. But then it rises rapidly, and by the time you're about 4 times nuclear matter densities, it exceeds 1/3. And then presumably we know as you go to asymptotically high densities, it has to go back down to 1/3. This is really amazing that you're changing the degrees of freedom between non-relativistic degrees of freedom and relativistic degrees of freedom. And if the sound velocity squared or the conformal anomaly or whatever turns out to indicate this is really a massless theory which is describing this, it's a strongly coupled scale invariant theory, which might even get people who are doing ADS, EFT things excited. So next slide. There's a consequence of the sound velocity squared becoming close to a third. For a zero temperature Fermi gas, the sound loss is given by the baryon density divided by the derivative of the baryon density with respect to the baryon chemical potential times the baryon chemical potential. What that means is, roughly speaking, that the change in the baryon chemical potential divided by the baryon chemical potential is the order of the sound velocity squared times the change in the baryon density over the baryon density. Now, if the sound velocity squared is of order 1, and the change in the baryon density is of order 1, you see that that generates a change in the baryon chemical potential, which is of the order of the baryon chemical potential you started with. Well, at low densities, the baryon chemical potential is of the order of the nucleon mass. Therefore, the change in the baryon chemical potential is of the order of the nucleon mass. That doesn't sound so surprising, but if you think about non-relativistic nuclear matter theory, it's very surprising, because in non-relativistic nuclear matter theory, the baryon chemical potential minus the mass is basically the typical kinetic energy in a Fermi gas. And that's of the order of 100 MeV, not of the order of the nucleon mass. So what's happening is that the system is becoming relativistic very, very quickly, and the chemical potential is changing very rapidly. Now, in a first order phase transition, you know that you're supposed to hold the chemical potentials fixed while you vary the energy density. Here it looks like the opposite is happening, that the chemical potential is changing rapidly while the baryon density or the energy density is staying roughly fixed. Okay, the large sound velocities will require a very large intrinsic energy scale, and that has a consequence also. Because if you try to make a relevancy gas of nucleons where the Fermi momentum was of the order of the nucleon mass, that would be corresponding energy density, which would be 100 times the energy density of nuclear matter, and that's too large. So the question is, how can you have these relativistic neutron degrees of freedom without the density of the matter going through the roof? And that's what I'm going to try to describe in the following slides. So next slide. Before I do that, I want to review sort of the technique which makes all of this understandable. The technique is the large NC limit. And the large NC limit explains patterns which you see in when you try to calculate the equation of state of strongly interacting matter. So it's useful to think that the course might be large, NC goes to infinity. And in this limit, quark loops are suppressed by 1 over NC. Quark pair production cannot short out the long-range potential in the vacuum, so the risk confinement is well-defined quantity. Baryons are heavy, they're made of NC quarks, so their mass is order NC, and their interactions are very strong because they have NC quarks in them. And that cancels out suppression by the factors of order over NC. On the other hand, mesons are weakly interacting because they only have 2 quarks, and quarks interact weakly. Their interaction strengths of order 1 over NC. So the theory of large NC is a theory of very heavy baryons, which very strongly interact, and mesons, which have typical masses that are very weakly interacting. Next slide. So what does high temperature world look like at 0 baryon density? I want to go back. Okay, thank you. The confining force is cut off at a screen associated with the polarization of thermal gluons. And you calculate that, and that's 1 over r squared divided by the tube coupling constant squared times g squared. The tube coupling constant squared includes the effects of NT, which you get from counting the number of gluons in that loop. So it's not quite the ordinary coupling constant it used to be. But that's the coupling constant which controls the large NC expansion. Okay, and because this is natural in terms of tube coupling constant, which is some natural coupling constant, doesn't shrink to 0 large NC limit, that means at some temperature, the order of the QCD scale gluons get screened, and because they get screened, because long-range force gets screened by gluons, then the system has a confinement-deconfinement transition. And a large NC, it has to be a real phase transition, because in the vacuum there really is confinement. It can be defined unambiguously. And at high temperatures, confinement disappears. Therefore, there's an order parameter, which is long-distance behavior of the force between heavy quartz. And that, in fact, changes at some temperature of order lambda QCD. Next slide. You can also understand this in terms of hadrons. At low temperatures, there's a hadron gas of very weakly interacting hadrons. Since if T is much less than lambda QCD, the density of hadrons is of order 1 in powers of NC because the mesons are color singlet, and therefore there's some order 1 of them in the system, and interactions are very weak. It's just simply weakly interacting gas of hadrons. But in large NC, it turns out that the spectrum, the density of states as a function of mass, grows exponentially, just like in the Hagedorn model. And what that means is that if you ignore interactions, okay, that density of states will rise, and the Hagedorn limiting temperatures, you can't go to any higher temperature. And of course, that gets cut off in large but finite NC, because if there was a gas of gluons, the density would be a order NC squared. And you can also go to an energy density, which is that scale with the gas of mesons. And with the gas of mesons, the mesons have cross sections which are order 1 over NC squared. And those interactions become big when the density is order NC squared. So because of this Hagedorn spectrum of rapidly rising densities of states as a function of mass, at some temperature, even in the hadron world, you see that the description in terms of hadrons have to break down. And there truly is a phase transition between orbital and plasma and hadron gas. So, the large NC limit, without thinking too hard, reproduces the qualitative features of what you expect for the confinement-deconfinement phase transition of QCD. That should give you some faith that the methods are, at least provide some qualitative insight. Next slide. So what about finite density or chaotic matter? Confinement temperature disappears because the device screening length becomes shorter than the confinement scale. That's what happened in finite temperature. And gluons gave a device screening mass which went like G squared to 2 times G squared, or pi radius squared, which goes like 1 over that. However, at finite density, at 0 temperature, there's also typical fermion or chemical potential associated with quark density, μQ, the chemical potential of quarks. μQ is baryon chemical potential divided by NC, because of course baryons have NC percent. Okay, however, if you do the same calculation, you calculate the device screening mass, it goes like mu squared quark, because that's the only scale and calculation of the device screening length. But because the quarks are weakly interacting, it goes like 1 over NC. And therefore, the device screening length gets no effect at all in the large NC limit at finite density. And because you're at 0 temperature, the contributions of gluons are the 0 temperature contribution. And therefore, strictly in the large NC limit, the theory is always confined. That should shock you, because the scale of chemical potentials can become huge compared to QCD scale. It can be 100 GeV. And if NC was large enough, the theory is still confined. The interactions, even though they're intrinsically weak, somewhere in the system there has to be strongly interacting particles, which are keeping the system intrinsically confined. Next slide. Okay, and that concept that you can have very high density matter and it's still confined leads to the ideas of quark ionic matter. So in the large NC limit, at finite density, the deconfinement chemical potential is roughly at mu quark is the order of square root of NC lambda QCD. So in fact, for finite or large NC, confinement does disappear, but it occurs at an enormously large scale. So in this plot, I try to show you what's going on where the deconfinement transition is at. If you have strict large NC limit, then there's a deconfinement transition at finite temperature, which is totally unaffected by the density of quarks. However, if you take large but finite NC, then from mu quark of order lambda QCD up to some scale of the order of square root of NC lambda QCD, the system's still confined. But then, as you go to larger and larger values of mu quark, eventually this temperature should shrink to zero. Okay, so the blue line shows what happens at large but finite NC, and the red line shows what happens at infinite NC. Next slide. Okay, how do I think about quark-ionic matter? Well, to the right of that dashed blue line, okay, there's an unconfined gas and quarks and gluons. That's what we typically call the quark-gluon plasma. And at very low densities and low temperatures, we of course have confined mesons. And you can ask about nucleons in that system. Are there any nucleons in that system? If you calculate the density of baryons, the density of baryons is roughly the exponential of u baryon minus E divided by T. And let's do this at finite T. If we make mu B less than E, okay, then you see that this term is the order of E to the NC mu Q minus E Q. If mu Q minus E Q is of order subtype of the QCD scale, or any scale for that matter at all. When T goes to zero, this is exponentially suppressed. And what that means is that low temperatures and low densities aren't any baryons present. And that's quite reasonable because baryons are very massive. And if you're low temperatures and low densities, they should be exponentially suppressed because their mass is so large. However, I can make a chemical potential, baryon chemical potential larger than the nucleon mass. And if I do that, then this term is no longer exponentially suppressed. So there's some intermediate region where the chemical potential is the order of the nucleon mass up to some very high scale, which is characterized by the square root of NC, where there's a confined gas of quarks, baryons, mesons, and blue balls, and really are baryons present. And that's what we call quark-ionic matter. It's this region where you've got high enough density so that baryons are really present and it's still confined.